Who joined now? Just message. Today we are doing numericals on atoms, okay? So I will start now. I consider here you know the theory about the atoms, okay? So I will start the session now. Here first write down the problem. Calculate the shortest wavelength in the Balmer series. Okay, write down the first problem. I hope you know. Write down the first problem. I hope you know the theory about the atom. Okay, so while explaining the numericals also I will teach the part related to that. Okay, calculate the shortest wavelength in the Balmer series of a hydrogen atom. Calculate the shortest wavelength in the Balmer series of a hydrogen atom, full stop. In which region, bracket write down, infrared, visible or UV of hydrogen spectrum does this wavelength lie? Where does this wavelength lie? Okay, I will repeat this question. Calculate the shortest wavelength in the Balmer series of a hydrogen atom, full stop. In which region, inside the bracket, infrared, visible, UV, bracket complete, of a hydrogen spectrum, where does this wavelength lie? Okay, so this is the question. Read the question first properly. So they are interested here in a shortest wavelength. Okay, so here also we are using some logic. So here first highlight which point. First is the shortest wavelength. Okay, shortest wavelength. Okay, so next part, that is they are giving this as a Balmer series. Very important, this you should know. Balmer series. So this is a Balmer series, and Balmer series में final is always 2. Okay, and n initial is from infinite. Okay, so we are here, this is a hydrogen atom. Okay, they are saying Balmer series of a hydrogen atom. So in this case the final is nothing but 2, and n initial stage is nothing but infinite here. So here they are asking shortest wavelength. So we know that the formula 1 by lambda is equal to r. R is nothing but here Rydberg's constant. Inside the bracket 1 upon nf square minus 1 upon ni square. Okay, this formula we have. So here they are asking shortest, that is nothing but here lambda minimum, and this is nothing but r inside the bracket nf minus ni square. Okay, so this is what we can modify it, and then substitute the value. Balmer final is always 2. Okay, for shortest, and then we can substitute here 1 by lambda min. So Rydberg's constant is nothing but 1.1 into 10 raised to positive 7. Okay, 1.1 into 10 raised to 7. Nf is nothing but 1 by 2 square, and Ni is nothing but infinity. Okay, infinity, that means 1 by infinity is 0. So 1.1 into 10 raised to 7, and this 1 by 2 square is nothing but 4. Okay, so this is lambda, 1 by lambda minimum. So we can write here lambda minimum is nothing but 1.1 into 10 raised to 7. Oh, not 1.1, 4 upon, we can write 1.1 into 10 raised to 7. Okay, now do this calculation and simplify. So I will write here 40 by 11 into 10 raised to minus 7, and this we will get something 3.63. 3.63 into 10 raised to minus 7 meter. Okay, 10 raised to minus 7 meter. And remember, Balmer series always lie in the visible region. Okay, this is always in the visible region. This is very important. Understood? This is very important. If you don't have the notes with you, just check once. Okay, copy this or give me some time. I will explain you all 5 ranges we have. Okay, so total we have 5 series. We have total hydrogen spectra, and in that hydrogen spectrum there are total 5 series are there. First is a Lyman, second is a Balmer, third is Paschen series, and fourth is bracket series, and last is P fund. Okay, you can take a screenshot and I'll explain that all 5 because we require this, okay, for this solving numerical. So everyone copied this, or you can take a screenshot. Now, someone copy us. Yeah, I have. Okay. So total we have 5 series over here. Write down one by one. First you can write down Lyman series. Okay. First you can write down Lyman series. Okay. And for Lyman series, it jumps to first orbit. Okay, always it jumps from infinite to first orbit. Okay, so n final is nothing but 1. Okay, and n initial, okay, means where it will come from. So it will come from maybe 2, maybe 3, maybe 4, and so on up to infinite. It's very important. Okay, and this is always lying in UV region. Okay, can you getting? Lyman series means the electron always jumps from infinite to 1. That means its final state is nothing but 1, and it can jump from second orbit or third orbit or 4 or infinite. Okay, and it is always lying in the UV region. This is very important. Then next we have Balmer series. Okay, Balmer series is always the electron jumps to the second orbit. Okay, the electron jumps to the second orbit, or maybe it comes from third, fourth, fifth, and so on up to infinite. Can you get in this? And this is always lying in between visible region. This is UV and this is visible. This is in the visible region. Okay, getting this? Okay, and then we have third, that is Paschen series. Paschen series. Okay, in Paschen series always electron jumps from infinite to third orbit. Okay, but it will not come from 1 to 2 or 2 to 3. No, it always comes from infinite to 3, and here n initial may be 4, 5, 6 and so on. And it is always lying in the infrared region. Very important. This is always lying in infrared region. Understood? Then next is nothing but your bracket series. So in bracket series, NF is nothing but what? 4. That means electron jumps from infinite to 4, or it can come from 5, 6, 7 and so on up to infinite. Okay, and it is also always fall or lie in the infrared region. And last is nothing but we have P fund series. Okay, so here NF is nothing but 5 and Ni is nothing but 6, 7, 8 and so on. Okay, and in this case this is also lying in the infrared region. So this is very basic information about all the 5 series. Okay, first we have a Lyman series, then we have a Balmer series, then Paschen, bracket series, and last one is P fund. So what we have to remember, always remember this in a sequence wise, don't miss, okay? Otherwise you can forget all the NF. Once you know the NF, then initial calculation is very easy, okay? So Lyman, it always jumps, means electron jumps from infinite to first orbit. In Balmer, always electron jumps from infinite to 2, and here in Paschen, electron is always jumps from infinite to third orbit, and in bracket series, electron jumps from infinite to fourth orbit, and in P fund, it jumps from infinite to 5. Okay, and only first Lyman series is only lying in between UV, and Balmer is in a visible. Rest other, means Paschen, bracket, and P fund are lying in the IR region. Can you getting this? Okay, and whenever they are asking shortest wavelength, okay, remember what I am saying, whenever they are asking the shortest wavelength, in that case you have to take initial is nothing but infinite. Always remember, whenever they will ask for any series, shortest we are taking it as a infinite. So while calculating, you have to take Ni is nothing but infinite. Can you getting this what I am saying? Can you able to understand what I am saying here? Can everyone able to see this? Okay. So here shortest wavelength means we are taking initial, and initial is infinite, and whenever they are asking longest, okay, whenever they are asking longest, then NF is nothing but what? Right after the second. Means suppose they are asking calculate the longest wavelength for a Lyman series. So in Lyman series, it is lying where? In 1. So you have to take an initial here as right after 1 is 2. Okay, suppose in Balmer series just now we did. So if they are asking longest, then you have to go for 3. Okay, if they are asking shortest, go for infinite. Okay, in Paschen also, if they are asking to find out the longest wavelength, then you have to go for 4. And if they are asking shortest, then go for the infinite, because here we are doing calculation 1 by lambda. Okay, so bracket also, if they are asking for shortest, go for infinite. If it is longest, then go for 5. Getting? So like that in P fund also, shortest infinite and initial longest is nothing but 6. So these are the tricks to do all the numericals based on this kind of series. Okay, so take a screenshot of this. This is very, very important. Okay, this is very important. I hope everyone took this screenshot. Okay, chalo. So write down next problem. When, or wait, write down. Yeah. Write down when H alpha line, okay, H alpha. So write down this as a H alpha line in the emission spectrum. When is H alpha line in the emission spectrum of a hydrogen atom, obtained question mark. Calculate the frequency of a photon. Calculate the frequency of the photon emitted. Calculate the frequency of the photon emitted during this transmission or transition. During this transition, I'll repeat this. When is H alpha line in the emission spectrum of a hydrogen atom obtained? Calculate the frequency of a photon emitted during this transition. Okay, question is very important. Make 2 star IMP. Okay, so student don't know what is H alpha. Okay, because we learn only Lyman, Balmer, Paschen and T-Fund series. No one knows what is H alpha line. Okay, or H alpha series. So H alpha whenever comes, that means that is related to Balmer only. Okay, remember, if H alpha comes, then that means it is related to Balmer series. Remember. Okay, write down somewhere here, H alpha is nothing but what, related to Balmer series. Okay, so once we know that it is Balmer series, so we know that NF is also 2. Now we have to decide Ni. Okay, because here what kind of frequency they are asking, check. When H alpha line in the emission spectrum of a hydrogen atom is obtained, calculate the frequency of the photon emitted during this transition. So H alpha is Balmer series, and in this case by default we are taking NF as a 2 and Ni we are taking it as a 3. That means they are asking us for a shortest, that means they are asking for the longest wavelength. Okay, they are asking for the longest wavelength. So here we know the wavelength formula, but we don't know frequency. We are getting lambda, that means from that we can calculate frequency. Okay, so here this is, make it IMP. Whenever H alpha comes, then they are not asking whether it is shortest or longest. By default you have to take NF. By default you have to take NF as a 2 and Ni as a 3. Okay, so here that means we are calculating longest wavelength for the Balmer series. So write down the formula here, 1 by lambda is equal to R is into 1 upon NF square minus 1 upon Ni square. Okay, getting this? So always write the formula first, then write down the H alpha. Okay, these things you can keep ready. Redbox constant 1.1 into 10 raised to 7. NF is nothing but 2 square minus Ni is nothing but 3 square. Okay, so 1.1 into 10 raised to 7. So you can write 1 by 4 minus 1 by 9. So simplify this, 1.1 into 10 raised to 7. So 9 minus 4, 36. And then 1.1 into 10 raised to 7. 9 minus 4 is 5 by 36. And then simplify this. This is nothing but 1 upon lambda. So I will write lambda is equal to 36 into 10 raised to minus 7 divided by 1.1 into 5. Okay, so now do this multiplication, do this calculation. So once you simplify this, you will get lambda is nothing but 6.54. 6.54 into 10 raised to minus 7 meter. This is nothing but lambda. And we know that they are asking us frequency. Once you get the lambda, so we know that frequency is nothing but C by lambda. C is nothing but velocity of a light, and that is nothing but 3 into 10 raised to 8 divided by 6.54 into 10 raised to minus 7. So do this calculation, simplify it, check how much is the answer you are getting. I'll give some time, solve this. Check the frequency, how much it is. Can you people getting this? Everyone is getting what I am saying? H alpha, these points you can note it down properly. Okay, so do this calculation. After calculating this, you will get the answer 4.57. Okay, you will get here 4.57 into 10 raised to plus 14 hertz. Okay, frequency we are measuring in terms of hertz. Okay, getting this? Check, if R we are taking 0.96, then also values are little bit varying. Some are taking 1 into 10 raised to 7. So in exam they will mention this value also. Okay, So according to this, we are getting frequency 4.57 into 10 raised to 14 hertz. Okay, understood what is H alpha means? H alpha is always related to Balmer series, and here Balmer series means electron can jump from infinite to 2, and alpha means we have to calculate here longest waveform. So we are taking Ni as 3. Right after 2 is nothing but 3. Getting this? Okay, I hope everyone took the screenshot or some of you got the answer also. So write down next question. Write down next question. The radius of the nth orbit. The radius of the nth orbit in Bohr's model. In Bohr's model of hydrogen atom is proportional to write down first option n square small n square, second option 1 upon n square c n only n, and last option 1 upon n. Okay, so I'll repeat this question. The radius of the nth orbit in the Bohr's model of hydrogen atom is proportional to first bit n square, b 1 upon n square, c n, and last is 1 upon n. Many of you got the answer. That is nothing but how much? How much is the answer? We know that Bohr's nth radius is nothing but what? What is the formula? We can write no. Rn is nothing but R naught into n square. So Rn is nothing but what here? N square, no? So the option is 1, that is A. Okay. So this Rn is what? Directly proportional to n square. So option A is the correct option. Getting this? Understood? Okay, chalo write down next question. The potential energy of an electron, in the second excited state, the potential energy of an electron in the second excited state in hydrogen atom is first option is given A minus 3.4 electron volt, B minus 3.02 electron volt, minus 3.02 electron volt, C minus 1.51 electron volt, and last option minus 6.8 electron volt. I'll repeat this question. Potential energy of an electron in the second excited state in hydrogen atom is A minus 3.4 electron volt, B minus 3.02 electron volt, C minus 1.51 electron volt, and D minus 6.8 electron volt. Okay. So sometimes this question comes for 2 marks or sometimes come for 1 mark also. So this is also very important question. So here the potential energy of the electron in the second excited state. So whenever they are saying second excited state, that means we are taking here second excited state as 3. Okay, not 2. Suppose they are asking ground state, that means we are not taking 0. Ground state means 1. Okay, third excited state means we are taking n is equal to 4. Very important, don't forget this. So here n is equal to 3 and ground state we know 1. Okay, so here second excited state, then they are asking here potential energy. So we know that here total energy is nothing but what? Minus 13.6. upon n square electron volt. Correct? This is what we have the formula. So substitute here minus 13.6 and n is nothing but here 3 square, that is 9. So minus 13.6 upon 9 and this value comes around minus 1.51. Correct? So we are getting here minus 1.51 electron volt. Okay? But this is not my answer. In option also this option is given, but this is total energy. So in Hari-Bareilly don't take minus 1.51. They are asking here for potential energy, and we know that here one relation. Okay, total energy is nothing but what? Minus kinetic energy, and that is equal to how much? Potential energy by 2. Okay, so we are interested in potential energy. So you can write here total energy is equal to potential energy by 2. Therefore, potential energy is equal to 2 into total energy. So 2 into, I have here minus 1.51 electron volt. So that is nothing but 2 here 0 3 minus 3.02 electron volt is the answer. So which option is the correct? B option is the correct option. Can you getting this? Can you getting how I am solving? Can everyone is getting? At least reply something. Yes, no, or all are sleeping nicely. Okay. Chalo, write down. Take a screenshot. Write down next question. The radius of the innermost electron orbit. The radius of the innermost electron orbit of a hydrogen atom is 5.3 into 10 raised to minus 11. 5.3 into 10 raised to minus 11 meter. The radius of the n is equal to 3 orbit is. Okay. So I will repeat this. The radius of the innermost electron orbit of a hydrogen atom is 5.3 into 10 raised to minus 11 meter. Full stop. The radius of the n is equal to 3 orbit is. Write down first option. 1.01 into 10 raised to minus 10 meter. 1.01 into 10 raised to minus 10 meter. Second bit 1.59 into 10 raised to minus 10 meter. C 2.12 into 10 raised to minus 10 meter. Last option 4.77 into 10 raised to minus 10 meter. Okay, so I will repeat the option one more time. 1.01 into 10 raised to minus 10 meter. B 1.59 into 10 raised to minus 10 meter. Then 2.12 into 10 raised to minus 10 meter. D 4.77 into 10 raised to minus 10 meter. Okay, so here just now we did one MCQ based on the Bohr's radius. So that same we have to use that formula here. So write down, those who know this, they can start solving and then verify the answer with me, or you know the options, so you can verify with the options. Okay, so here we know that hydrogen atom Bohr's radius is given, that is R0 is nothing but 5.3 into 10 raised to minus 11. okay, minus 11 meter. This is what the R naught. Okay, then they are saying n is equal to 3. So it is given everything. So Rn is nothing but n square into R naught. Getting this? Okay, sorry. R naught is nothing but n square into Rn. Okay, so no, Rn only, sorry, n into n naught. So here n is nothing but here 3 square, R naught is given 5.3 into 10 raised to minus 11. So 3 square is nothing but 9, 9 into 5.3 into 10 raised to minus 11. So okay, 47.7 into 10 raised to minus 11. If you shift the decimal, then you will get here 4.77 into 10 raised to minus 10 meter. So now check the option, which option is correct. Yeah, that is 10 raised to, yeah, last one, 4.77 into 10 raised to minus 10. Okay, calculate. Getting this? Okay, now write down next one. The short wavelength limit for the Lyman series of the hydrogen spectrum is 913.4 Armstrong unit. Calculate the short wavelength limit for the Balmer series of the hydrogen spectrum. Okay, so we'll repeat this question. The short wavelength limit for the Lyman series of the hydrogen spectrum is 913.4 okay, 0.4 Armstrong unit. Calculate the short wavelength limit for the Balmer series of the hydrogen spectrum. Okay, so see, short wavelength limit for the Lyman series is given. Question, see what is the question? Short wavelength limit for the Lyman series is mentioned. Okay, and that is nothing but how much? 913.4 Armstrong unit. Means here directly wavelength for the Lyman series is given, that is 913.4 Armstrong unit. Then they are asking from this, calculate the short wavelength limit for the Balmer series of the hydrogen atom. So how can you calculate now? Check. How can you do this? Write down here. Try yourself also. I will try to write the given quantities here. Okay. So here Balmer means we know that 1 by lambda is nothing but R inside the bracket 1 upon Nf square minus 1 upon Ni square. Okay. So the short wavelength limit for the Lyman series is given. So we know that Lyman series Nf is nothing but 1, and they are saying short wavelength, then that means we are taking Ni is nothing but what? Infinite. Getting this? So here can we write for Lyman? For Lyman we can write 1 upon lambda is nothing but R inside the bracket 1 upon 1 square minus 1 upon infinity, that is 0. So 1 by lambda is nothing but R. 1 by 1 square is nothing but what? 1 only. Okay. So here we get this much. But we know no, here the value of the short wavelength is given. How much? Lambda is given 913, no, 0.4 Armstrong unit. This much is what the value given. So lambda is given. That means, can we write here? We can make here lambda is nothing but 1 by r, and this value is nothing but how much? 913.4 Armstrong unit. Can I write it like this? Okay. So I'll erase this step. This is given actually. Okay. Once you get this, then you can go for Balmer series. And here they are asking for Balmer series shortest wavelength, no? Yeah, calculate the shortest wavelength limit for the Balmer series. Okay, so you can go for Balmer now. So we finish the work for Lyman. Now we can move towards the Balmer, and they are asking for shortest wavelength. Shortest wavelength. So again, for shortest wavelength Balmer series, see, I will write it as 1 upon lambda b is nothing but r, 1 upon nf square minus 1 upon ni square. Okay, shortest again infinite, and we know that Balmer nf is nothing but 2. So we can write r 1 upon 2 square minus 0, infinity, no, so 0, and 1 upon lambda b. Okay, so here we can write it as 1 upon lambda b is nothing but r by 4. Can you getting this? Okay, so we are interested in lambda b, so we can write it as 4 by r. Can you getting this? Okay, so now simplify this 1 by r, and here 1 by r is nothing but this. So 4 I will write it as 4 into 1 by r. Okay, so that means we can write it as 4 into 913.4 Armstrong unit and calculate the answer. Okay, so this will come 1. Okay, 36536. Okay, 3653.6, and answer will remain in Armstrong unit. If you want to convert into meter, 3653.6 into 10 raised to minus 10 meter. So this is what the answer. Okay, this is 3-mark question, very IMP question. All the values are given for the Lyman. Okay, and they are asking for Balmer. Getting? Understood? Getting this? All you are writing the questions now which I am dictating. Copy this, finished. Okay, then after that we can go for okay, write down one more MCQ. Which of the following statement is not correct? Which of the following statements is not correct according to the Rutherford model? According to the Rutherford model. First option, most of the space inside the atom is empty. First option, most of the space inside the atom is empty. B, the electron revolve around the nucleus. The electron revolve around the nucleus under the influence of Coulomb force acting on them. Third bit, most part of the mass its positive charge and its positive charge are concentrated at the center, and positive charge are concentrated at its center. And last bit, the stability of an atom was established. The stability of an atom was established by this model. Okay. So I will repeat the question once again. Which of the following statement is not correct according to the Rutherford model? First bit, most of the space inside the atom is empty. B, electron revolve around the nucleus under the influence of the Coulomb force acting on it. Most of the part of a mass of the atom is positive charge and are concentrated at its center. And last, the stability of an atom was established by the model. So they are asking which is a not correct statement. Okay, they are asking which of the following statement is not correct according to the Rutherford model. So in Rutherford model there is a no stability is achieved. So answer is last bit, the stability of an atom was established by this model. That is the false statement. Can you getting this? Okay, so today I will stop here. Okay, I can again tomorrow evening I will continue with this. Okay, I will end this session today. At least you can revise the theory for the atom. Okay, bye.
किती वाले
व्ह्यू जाऊ दे, एक तास पण झाला की नाही माहिती नाही मला.
झालास
नाही झाला समय.
अरे